Okay, so for one, our new unit, the first section is about implicit differentiation. So I'm going to read through this little passage really quickly. It says that for most of our algebraic study of math, we've dealt with functions. And we didn't take pre-calculus, but in Sec Math 3, Sec Math 2, you guys talked about two different types of equations that relate x and y to each other. They're explicit equations and implicit equations. Explicit equations in x and y is when y is isolated on one side of the equation and it equals an expression that is completely in terms of x. So when you look at an explicitly defined equation, you can explicitly tell if it represents a function or not. So for example, when you look at y equals the square root of 25 minus x squared, you know that for every x value, there is only one y value, which makes this a function. But when you see y equals plus or minus the square root of 25 minus x squared, for every x value, there are two y values, the plus and the minus version, which means this is not a function. So explicit equations have y isolated. Implicit equations are different. Typically, they do not have y isolated on one side of the equation, and it's usually either impossible or very difficult to isolate y, which is why it's not isolated by itself. Often there is a power on the y term in the equation, and both y's and x's might appear throughout the whole equation. So for example, x squared plus y squared minus 2x plus 4y plus 16 equals 0 is the equation of a circle. And we'll look at that again in a second. So calculus is where we can do things with these implicitly defined equations. So in this lesson, we're going to see how we can take the derivative of functions or equations that are implicitly defined. Okay, so we're going to use an alternative notation for the derivative that we've seen before. So instead of just using the prime notation like f prime or y prime, we're going to be using the dy dx notation for this unit, or this section at least. Okay, so because calculus is founded by two different people, we have all of these different notations for the same thing, which is why we are going to be using a different notation here. So to get started thinking about implicit differentiation, let's first talk about differentiating that equation y equals the square root of 25 minus x squared. So I'm going to kind of split my page in two for a second. Okay, so this is an explicit equation because y is isolated. And the equation y equals the square root of 25 minus x squared. Let's take the derivative of this, or find dy dx. In order to do that, I never want a square root in my problem. If ever I'm taking the derivative, we don't want radicals. We always want to change them to exponents. So this is 25 minus x squared to the 1/2. So now we're going to find dy dx. Okay. This is a chain rule problem. The outside equation is u to the 1/2. So the derivative is 1/2. And then remember, we plug in the same thing on the inside. And then we have to multiply by the derivative of the inside, which is negative 2x. Okay. Now I just want to clean it up a little bit. So we have dy dx is equal to 1/2 times the square root of 25 minus x squared. I just rewrote that first piece, and then times negative 2x And I'm going to write it over 1 because I want to combine this to be one fraction, not two separate fractions. So our final answer, dy dx, on top we have negative 2x, and on bottom we have 2 times the square root of 25 minus x squared. Okay. We've done stuff like this before. We know how to use chain rule. We can take the derivative when y is by itself. And the notation for the derivative of y, one of the notations, is dy dx. Or we could also say y prime. They mean the same thing. But we're going to be using dy dx in this section. Okay. Now let's differentiate the implicit form of this equation. So these equations are equal to one another. They mean the same thing. It's just now y is not isolated by itself. So this is the implicit form of the same equation. And we have x squared plus y squared equals 25. If you were to get y by itself in this equation, you would see that you would get the square root of 25 minus x squared. So they're the same thing. One just has y by itself. Okay. When we differentiate this, we always, and I'm going to make a note here, star, highlight, circle this, treat anything that has a y as a chain rule. Okay. Treat y as a chain rule in terms of x. Okay, that's what dy dx means. We're taking the derivative of y in terms of x. So we're going to treat anything that has y in it as a chain rule. So if it's just y by itself, okay, let's think about that. For example, if I just have y all by itself, the chain rule, the derivative of the outside, well, it's just the function y, so the derivative of the outside would just be 1. Okay. Evaluated at the inside, well, because there's no x to plug it into, it's just 1. But then I have to still times by the derivative of the inside. So I'm timesing by the derivative of y in terms of x. So I'm going to be multiplying by dy dx. So y prime is equal to 1 times dy dx, which is why y prime and dy dx are the same, just different notations. Okay. So when we take the derivative of this implicit function, x is treated the same. We can do the derivative of powers and quotients and products just like we have been when x is involved. But if y is involved, we're going to have to do that chain rule. So that first piece, taking the derivative of x squared, just like normal, is 2x plus, now the derivative of y squared, kind of like what we would do with an x, it would be 2, the power rule, bring that power out front, but the inside function, because we're doing a chain rule, is y. And then times by the derivative of the inside. So whenever we have y, when we're taking the derivative, we're also going to see dy dx. Equals, and then we would take the derivative of the other side as well. The derivative of 25 is 0. Okay. So we took the derivative of y squared was 2y times dy dx, where y is that inside function and the outside function is something to the second power. Okay. Now I want to get dy dx by itself, because that's what it means to differentiate. We want dy dx by itself here. So I'm going to subtract 2x from both sides. So we end up with 2y dy dx equals negative 2x. And then, give me one sec. Divide by 2y. so that dy dx is equal to negative 2x over 2y, which is also just negative x over y. So you can see that the derivatives are not the same, but the derivative of the implicit function is y, has y in it. That's why they're not the same, because you can see, and actually we could even simplify this explicit derivative to just be x over the square root of 25 minus x squared. So the reason they're not the same is because the implicit form has y in our derivative, negative x divided by y. Oops, I forgot the negative there. The explicit form has negative x over square root of 25 minus x squared. But we know, and I'm going to draw a big arrow here with a highlighter, y is equal to the square root of 25 minus x squared. So we could replace the square root of 25 minus x squared with y, and it would be the same as our implicit differentiation. So we're getting the same answer. One just has y instead of what y is equal to. Okay. So implicit differentiation really is just chain rule of y. Let's look at another example. Okay. So let's look at this graph of the circle here. We want to write the equation of the circle in implicit form. So remember, implicit means that it has x and y on the same side. Okay. So if you don't remember the equation of a circle is x minus h squared plus y minus k squared equals r squared. And the hk is the center of that circle. Okay. So the center of this circle is right in here. And that point is 3, negative 2. And the radius of this circle, if I go from the center to one of the edges there, that's 5. Okay, so the equation of this circle would be x, and since it's to the right 3, it still looks like minus 3 plus, and then since we're going down 2, it's y plus 2. And then r squared is 25. Okay. That's not something that you necessarily have to have memorized. So you don't have to memorize the equation of the circle, but it's good to know in case you come across a problem like this, but it's not required to be memorized here. Okay, so we have the equation of the circle in implicit form because x and y are on the same side of this equation. Now let's implicitly differentiate this equation so that we can have the derivative, or dy dx. So we have a whole lot of chain rule going on in this when we take the derivative of this equation here. So the first piece, the x minus 3 quantity squared, the derivative of that is a normal chain rule. Take the power out front, the inside stays the same, and then you multiply by the derivative of the inside, which is 1. Plus, same idea here, we're going to do a chain rule, but when we multiply by the derivative of the inside, the derivative of that y will be dy dx. So the 2 comes out front, the inside stays the same, and then I multiply by the derivative of the inside. And just like that example I showed you up here on the side over there, y prime is equal to 1 times dy dx. That's the derivative of the inside here. and then equals, the derivative of 25 is 0. Okay. We're going to clean this up a little bit and get dy dx by itself. So, cleaning it up a little bit, this is just 2 times x minus 3 plus 2y plus 2 dy dx, and it still equals 0. I'm going to subtract this 2 times x minus 3 from both sides. So we get 2y plus 2 dy dx equals negative 2x minus 3. And then to get dy dx by itself, divide by 2 times y plus 2. The negative 2 and 2 are going to simplify out, so we just end up with dy dx is equal to x minus 3 over y plus 2. Negative. Sorry, I forgot that negative 2 on top. So because it was easier to do differentiation with x and y on the same side, now we can use implicit differentiation to do that. It would have been much more difficult to try and solve that equation up above for y and then take the derivative. You would have ended up with a bunch of quotient rule and power rule with square roots and radicals. So it's just a lot easier now. We know how to take the derivative without having y by itself. Okay. So we're still going to be looking at this circle for a minute, and we're going to fill in this table. We're going to find the value of dy dx at each of the points that are given, and we're going to draw those tangent lines on our graph on that circle. Okay. So we're going to be using this dy dx to fill in that table below. So if I'm looking at 0, 2 as the point, then dy dx would equal negative 0 minus 3 over 2 plus 2, which is 3 over 4. Okay. So I took 0, 2 and plugged it into dy dx from above. So let's go ahead and draw. I'm going to erase that radius line here. Let's go ahead and draw that tangent line on our graph. So the point 0, 2 is right here. Okay. It's a positive slope of 3 over 4. You can use your slope counting boxes that we've done in the past to draw this on here. Draw some extra points on here. I'm going to draw it dotted. And you can see that tangent line. Okay. Let's do the next one. 3, 3. So dy dx equals negative 3 minus 3 over 3 plus 2, which is just 0. Remember, when we have a derivative equal to 0, that means we have a horizontal tangent line. So at 3, 3, which is right at the top of that circle, we have a horizontal tangent line. Next, dy dx equals negative 8 minus 3 over negative 2 plus 2, which gives us negative 5 over 0, which is undefined. And whenever we have an undefined derivative, that means we have a vertical tangent line. So at 8, -2, it's right on the side there, we have a vertical tangent line. Okay. You can speed up through this part of the video if you want to quickly solve for these values and draw on those tangent lines. Okay. So we have -3 minus 3 over -7 plus 2, which is another 0. So at 3, -7, we have another horizontal tangent line. And then dy dx of 6, 2, we have -6 minus 3 over 2 plus 2, which is 3 over 4 again. 6, 2, -3 over 4. Like, that does not make sense. So 6, 2, our slope is negative. Right there, we have -2 minus 3 over -2 plus 2, which is undefined. So at -2, -2, which is over here on the left side, we have another vertical tangent line. And then last one, 6 minus 3 over -6 plus 2 is, where am I? Oh, -3 over -4, or 3 over 4. So 6, -6 right here. See that tangent line. Okay. So that implicit differentiation is still letting us find the slopes of those tangent lines. We can just do it without having to solve for y now. Okay. Moving along, let's do some more practice finding dy dx then. So we want to find dy dx for each of these following implicitly defined equations. So on that first box at the top there, we have y squared equals 2x plus 3y. So when we take the derivative, we have to take the derivative on both sides of the equation. So the derivative on the left side is a chain rule, remember, because we do chain rule whenever we see y. So it's 2y times the derivative of the inside, which is just dy dx, equals, x is the same kind of derivative we've been dealing with, so just 2 plus, and then the 3y, when we do chain rule on 3y, the derivative of the outside is just 3. And we don't have anywhere to plug the inside back into, so remember how I say when you do chain rule, you have like 3x. Some of you guys were doing 3 times x still when you did chain rule, but the derivative of the outside is just 3, and then times the derivative of the inside. So now we want to get dy dx all on one side and then solve for dy dx. So in order to do that, I'm going to subtract 3 dy dx from both sides. So I end up with 2y minus, 2y dx. 2y dy dx minus 3 dy dx equals 2. Now on the left side, I have dy dx on both terms, so I'm going to factor that out. So I can take dy dx and factor it out of both of them, so I'm left with 2y minus 3. And then I can divide both sides by 2y minus 3. So I'm left with dy dx equals 2 over 2y minus 3. Okay. Let's do the next one. So on this next one, take the derivative of both sides. The derivative of 2x is just 2. And then we have e to the y. So we know that the derivative of e to the x is just e to the x. So when we do this one, this y, I'll highlight it here, is still acting as a chain rule. It still is considered an inside function. So when we take the derivative of this, we're going to have to multiply by the derivative of y, which is dy dx. So this derivative is e to the y. The derivative of the outside, e to the y, is just e to the y, times by the derivative of that y, which is dy dx. And then equals the derivative of x squared is 2x, and then minus the derivative of y squared, the derivative of the outside is 2y, times the derivative of the inside is dy dx. We want to get, I'll use a different color here, the pieces that have dy dx on the same side, because we eventually want to get dy dx all by itself. So I'm going to add 2y dy dx to both sides and subtract 2 from both sides so that I can do this all in one motion. And I'll end up with e to the y dy dx plus 2y dy dx equals 2x minus 2. So just like in that box before, each term on the left has dy dx. I can factor that out. And divide by e to the y plus 2y. So I end up with dy dx equals 2x minus 2 over e to the y plus 2y. Okay. Moving along, we're almost done with these notes. So on the next one we have 2xy equals 3y squared plus 2x. 2xy is a product rule, right? We have to do the derivative of the first times the second plus the derivative of the second times the first. So the derivative of that whole left side there, the derivative of 2x is 2. So the derivative of the first piece is 2 times the second function, okay, plus the derivative of y is dy dx times the first, and then we can do the derivative of the right side. So 2y plus 2x dy dx is the derivative of that product rule. And that equals the derivative of the right side, 3y squared. Just like normal, the derivative of the outside would be 6, and then the inside is y, times by the derivative of the inside, plus the derivative of 2x is 2. I'm going to rewrite this and kind of clean it up a little bit. So we would have 2y plus 2x dy dx equals 6y dy dx plus 2. We want all of our dy dx's on the same side. and everything else on the other. So I'm going to subtract 6y dy dx from both sides and subtract 2y from both sides. So I'm going to end up with 2x dy dx minus 6y dy dx equals 2 minus 2y. Factor out dy dx and divide both sides by 2x minus 6y. So we end up with dy dx equal to 2 minus 2y over 2x minus 6y. Hey, if you can, go ahead and pause the video and try the next one on your own. And we'll go through it together once you're finished. So again, this one has another product rule, right? That 3x squared times y is a product rule. So we're going to have to remember to do that when we get to that side of the equation. The derivative of the left side of the equation is easy because there's no y values on it. So we have 15x squared. And then derivative of 3 is 0. So that's it for the left side. Equals the derivative of 2y is 2 times the derivative of that inside piece, so dy dx. And then minus, and I'm going to put parentheses because now I'm going to do that product rule and I want to make sure that negative gets distributed to everything. So the derivative of the first piece, which is 3x squared, is 6x times the second plus the derivative of the second times the first. And then we just need to clean it up. So 15x squared equals 2 dy dx minus 6xy minus 3x squared dy dx. Okay. Dy dx's are already on the same side, but I do have to get rid of that negative 6xy and move that to the other side. So I'll have 15x squared plus 6xy equals 2 dy dx minus 3x squared dy dx. And then factor out the dy dx and divide both sides by 2 minus 3x squared. So our final answer, and I'm going to switch it around, so dy dx is on the left, is equal to 15x squared plus 6xy divided by 2 minus 3x squared. And that's our final answer. Okay. So a lot of chain rule. We're going to have to really get good and comfortable with chain rule here. All right, last page. So for what values of x will the curve x to the third plus y to the third equals 4xy plus 1 have a horizontal tangent? Show your work and explain your thinking. So for something to have a horizontal tangent, remember that means that dy dx is equal to 0. So let's find what dy dx is and set it equal to 0. And pretty much that part of us saying dy dx equals 0 when we have a horizontal tangent line, that's the explain our thinking part. So let's do our implicit differentiation. So we have the equation x to the third plus y to the third equals 4xy plus 1. The derivative of the left side, we have 3x squared plus 3y squared times dy dx equals product rule. Now we have 4x, or sorry, I'll do it the same way I've been doing it. the derivative of the first one is 4 times the second plus the derivative of the second times the first. And then the derivative of 1 is just 0. So clean it up, get your dy dx all on the same side. So I have 3y squared dy dx, and then I'm going to subtract 4x dy dx to that side, equals 4y minus 3x squared. Factor out dy dx. And divide by 3y squared minus 4x. So we end up with dy dx equals 4y minus 3x squared over 3y squared minus 4x. So we did the implicit differentiation. Now we want to set this equal to 0 and solve. Okay. So really, if this whole thing is equal to 0, that means that the numerator is equal to 0. Or you could think of this as multiplying both sides by 3y squared minus 4x, so that denominator goes away. So really this is the same as 4y minus 3x squared is equal to 0. And then we're solving for x. Okay, so I'm going to get x by itself here. So 4y equals 3x squared. And actually, instead of getting x by itself, I'm going to stop here because we know what y is. Okay, we can solve for y. Hang on, sorry guys, I'm trying to follow my work from before. We're good to up to this point so far. Let's solve for y. Y equals 3/4 x squared. Okay, I was one step ahead. We're going to use this as y, and we're going to plug it into our equation. Okay, so we know that in order to have a horizontal tangent, y has to be equal to 3/4 x squared. Okay, we're going to use that and our original equation up here to figure out what x is when y is equal to 3/4 x squared. Okay, sorry, I jumped ahead one step, and I'm sorry if that was confusing. We're good to this point. All of this work is valid. Now we're going to take our answer that we just found, and we're going to use that original equation. So x third plus y to the third equals 4xy plus 1. And wherever I see y, I'm going to replace it with what we just found. Wherever I see y, I'm going to replace it with that value that we just got. So this would be x to the third plus 3/4 x squared to the third equals 4x times 3/4 x squared plus 1. Now I'm going to clean it up a whole bunch. We have x to the third plus, this is 27 over 64, x to the sixth equals, we we have now 3x to the third plus 1. That was our exponent rules. If you have an exponent to an exponent, you multiply them. That's how I got the 6. And then if you have an exponent times something with an exponent, you add the exponents. That's how I got x to the third on the right side. Now combine like terms, get everything to one side. We're going to end up with 27 over 64x to the sixth minus 2x to the third minus 1 equals 0. And I set it equal to 0 because if we're solving for x and we have a polynomial equation like this, we want it set equal to 0. And in order to solve this one in particular, I would graph this and find the zeros on your graph. So you could either use your graphing calculator or Desmos to graph this and find out what those x-intercepts are. And you will see that x is equal to about negative 0.77 and 1.73. Okay. So we used our implicit differentiation to figure out what y was so that we could plug that into our original equation. This y value that we found, y equals 3/4 x squared, is the y value only when we have a horizontal tangent line. So we put that in to find out when do we have a horizontal tangent line. It's at those specific x values. Okay. All right, let's do the next one. In terms of y, describe the values of x for which the same curve will have a vertical tangent line. So a vertical tangent line we know is when dy dx is undefined. Okay, so that's the explain our thinking portion. In this one, we're not solving for x as a number. It tells us to do it in terms of y. So it's okay for y to still be in our answer. Before they were asking for the exact x value. Okay, so we know what dy dx is. We solved that in the step before. So dy dx was equal to 4y minus 3x squared over 3y squared minus 4x. For this to be undefined, that means that the denominator is equal to 0. So 3y squared minus 4x is equal to 0. Now I just want to solve for x. So 3y squared equals 4x, and x is equal to 3y squared over 4. So when x is 3y squared over 4, our tangent lines are undefined. They're vertical. And we're good to leave it like this because it asked us to do it in terms of y. Okay, last two. In these two boxes, they're giving us curves and they want us to find d squared y over dx squared. Don't know if you remember this from when we talked about notation, but this right here is the second derivative. Okay, so both of these are asking us to find the second derivatives for these curves. So on this first one, we have y squared plus 2y equals 2x plus 1. Let's find dy dx first. So dy dx, we have 2y dy dx plus 2 dy dx equals 2. Factor out that dy dx. and we end up with dy dx equals 2 over 2y plus 2, which we can simplify those 2's and end up with 1 over y plus 1. Okay. I'm going to kind of draw a line here now. That was our first derivative. Now let's find our second derivative. So d squared y over dx squared, which is the derivative of dy dx. Okay. We're going to have to use our quotient rule here. So derivative, it's low d high minus high d low over low squared. So low is y plus 1. D high, so the derivative of the top is 0, minus high. D low, the derivative of the denominator there is just dy dx. All over low squared. Okay. When we find the second derivative, we don't want dy dx in our answer. So we just want this in terms of x and y. So when I say that I'm multiplying 1 by dy dx right there on the second part of the quotient rule, I want to replace dy dx with what we know dy dx is. We know that dy dx is 1 plus y over 1. 1 over y plus 1. So I'm going to replace it down here. So our second derivative, we have that first piece goes to 0. So 0 minus 1 times dy dx, I'm going to write as 1 times 1 over y plus 1 over y plus 1 squared. Okay. Simplify this a little bit. This is negative 1 over y plus 1 over y plus 1 squared, which is just negative 1 over y plus 1 to the third power. And that's our final answer. Okay. Last one, we'll do another second derivative here. So we have x squared plus y squared, wow, y squared equals 1. Okay, so first we got to find dy dx. So that's 2x plus 2y dy dx equals 0. So 2y dy dx equals negative 2x. So dy dx equals negative 2x over 2y, which is just negative x over y. That was our first derivative. Let's find the second. So d squared y over dx squared, which is the notation for the derivative of dy dx, equals quotient rule again. Here we have low d high minus high d low all over low squared. And again, we know that dy dx is negative x over y. So I am going to replace that. So this is equal to negative y plus x times negative x over y all over y squared. And now we just want to clean this up. So get a common denominator on the top. So this is, if I times negative y by y over y, I'll have negative y squared over y. Whoa, that y looked weird. Plus, or I guess minus, x squared over y squared. Common denominator on top there. So then simplify it even more. Here we have negative y squared minus x squared all over y squared. A fraction divided by something, so I can combine those denominators, which is just negative y squared minus x squared over y to the third. And that's it. So that is implicit differentiation. This is the video for these notes. I'm also going to post another support video. The videos I've been posting from YouTube, the person who does them is awesome. I think he has really great videos. So I'm going to post those as well as the AP Daily videos that are already on Canvas. You can take a look at those if you're still struggling with this topic. But this is it for our